can you see my screen of the slides?
Yes, we do.
Okay, great.
Yes.
Great, thank you. So yeah, let me start. Sorry, I'm not so familiar with this. Okay. Yeah, so let's start our seminar today about energy efficient building design in practice. The next one. So today we will have a 5 parts of this seminar. So part 1 is what is building energy efficiency and why. Part 2, how to achieve building energy efficiency. Part 3, energy efficient building design process. Part 4, like case studies. And part 5 is a related topic and wrap up. So we will try to take like a break, like 5 or 10 minutes, for example, every hour. And during the presentation, you can type your questions through the chat function of this Zoom, and we can discuss before each part ends. So like before we end each part, we can look at the chart and maybe discuss those questions if we have time, or if we have more time at the end of the webinar, we can like discuss all the questions you have. So I probably can answer questions like at the end of each part and at the end of this seminar. So the first is about what is energy efficient building, energy efficient design. Looks like because everyone is have some knowledge of that, so the answer is quite obvious for you. So so I can probably just skip that. Basically, just a building uses less energy for like the same function. So that's energy efficient. So for example, like here, the photo I put in this slides, it is like an energy efficient rating of a building. So this is an example, like for United States, like New York, the city, they require people to those building owner to post their rating level to at the entrance, like for example at the door of their building, to show the energy efficient rating. So the rating is based on the comparison. They got a score to compare between this their building and similar buildings in the database. So so that's the energy efficiency score. So that shows the energy efficiency. We'll talk about that the benchmark thing later, a little bit more later in this seminar. The next slide. So why we'll do energy efficient design? Because for based on the World Green Building Council, the data, building and the construction are responsible for like 39% of all carbon emissions in the world. So that's a huge percentage. And the carbon emissions really related to like climate change and the other issues like energy dependency and like economy. So improve building energy efficiency actually improve the triple bottom line. So we show that the triple bottom line here, that is like economy, social, and environmental, or we call alternatively call planet, people, and the profit. So basically, it's at the beginning, it was a business concept for measuring social and environmental impact. In addition to the financial performance for success. Later, it becomes the bottom line for sustainability. So, so for example, for energy efficiency, building with energy efficiency, they will like their energy use will impact like their like a cost or the economy of the a big like a picture of the economy, and also like people people use the building, and also the social like a group of people, more people, and also the environmental inside the building, and also environment of the planet. So that's the triple bottom line. So the succeed of the building also, if they succeed in all these three parts, that means that the building is like a succeed. So so that's the basic. We can talk about it more. So for example, the reduced energy use can reduce greenhouse gas emissions, and it can slow climate change. So arguably, the most impactful aspect of greenhouse gas emission reduction is to slow the climate change and benefit the environment. The climate change is a central cause of increased like a droughts, sea level rise, like a drastic weather events. For example, the forest fire here in the picture, and also the like more like a devastating effects like other things. So reducing greenhouse gas emissions is the #1 key to working towards the cleaner, greener, and the safer and the healthy society around the globe. So for the climate change, you can see this chart that shows the record from 1980 to like 2014, the event of all kind of climate events that increase substantially. For example, the light blue, like extreme temperatures, droughts, forest fire, they increase somewhat from the beginning, because at the beginning is much less here, and here that's much higher. And the medium blue, dark blue, like a flood and mass movement, is definitely much more. You can see here, and other things like local storm, tropical storm, like also increased. So that's I think the climate change is real. Some people probably do not believe that, but we do see that's is happened, and is that also still happen. So, and other aspects of climate change, like social and the economy impacts, like energy shortage, damages the infrastructure, like increasing the loss of the industry and the illness. For example, the hurricanes, like this picture, they got devastated millions of people, like leaving them in absolute poverty after those like hurricanes sweeping away their community, and also like droughts, like they shrink the harvest and cause like food crisis. The World Bank is warning, like if we don't do something immediately, the climate change could push like more like 100 million more people into poverty by 2030. So yeah, that's a pretty significant. And so another broader picture of this is like for the air quality and the people's health. The production and the use of the fossil fuel that we typically use for energy is also known as the dirty fuels. For electricity and generation and the transportation, not only the contribution to the climate change, but also cause like pollution and a health problem, and also destroy our wide place and have like toxic chemicals. So that picture here is the smog in a China city. So that caused by the coal burning for heating and like a cooking and electricity generation in winter. So they are considered the main source of both PM 2.5 and other pollutions. The majority of the PM 2.5 come from those complicated photochemical reactions between the numerous chemicals. So that makes the air like this. It's very unhealthy. The next slide, another thing of make energy efficient will like reduce the fossil fuel dependency. So that's also important, like because like economies and the national security vulnerability is also an issue. And most of the world fossil fuel reserves are controlled like by states and not by companies. So consequently, they can use this to control and exert a leverage over the consumers. Therefore, some states that perceive like themselves to be resource deficient will have an enormous incentive to acquire more resource to hedge against like a politically motivated thing, you know, and exert control over other states. So that's to gain more control of the energy. And too often, because it's like a one person gain and equivalent to another person lost the game, like called the zero-sum game nature of the game. So it's likely to be achieved through like wars and some territorial expansion. So that's really bad for like if we look at that as a station like a nationwide. So reliance on the non-renewable energy source is not sustainable and involves increasingly destructive extraction process on certain supplies, escalating market price and the national security vulnerability. So that's in the broad economy side and the political side, that's also related to that. And but we can, for less, we talk about those like broad impact, like but more like for a building level, we will definitely make energy efficient, will reduce the energy cost and reduce the operational cost of the building, and also like for a building level, it will also improve the people's comfort and the people's health. Not the health, maybe related to energy, maybe not related to comfort, but it definitely related to some comfort things when we talk about the design, and also related to the let me check. Yeah, it's mainly related to the cost. For people and at the building level, it's related more to cost. Sorry about that. And then for the people and the environment, that's more like a broad picture issue, and that requires like a collective effort of all the buildings or country. Like they do that and then they achieve that goal. So that's so why we do that energy efficient. So like for most of the cost concern, like if we don't have enough energy source, then we have to serve more people in the for like a more building to use it. So we have to make it efficient. So that's a very basic consideration at a small scale. So that's what is like building and it's part one. So we just skim through really quickly for this part. So we will I can't see any questions about this. Do you have any questions? Okay, we don't see any questions. So let's see.
There's a question in the box. Oh.
Okay, looks like we don't have questions. So let's talk about where's the slideshow? Let's talk about the next part, how to achieve building energy efficiency. Can you still see my screen?
Yes, we can.
Okay, great. Okay. Why my sorry about that. Why my screen just stopped? Looks like I cannot change. Oh yeah, okay. So here is the chart of the we talk about today about the energy efficient design method. So we basically we'll have 3 steps for a typical energy efficient design in the building. The first step would be like reduce building energy loads. So we try to reduce building energy loads first, and then after the load is reduced, we apply a method to optimize the efficiency of the system. So, and then we apply the design of the efficiency of the system. And then after that, we got a low loads and low efficiency, high efficiency of the system. We got a minimize the energy use of the building. And then we will think about apply the renewable energy. So that's the last step to optimize the energy performance and of the building. And then in the next part of the section, we will also talk about the integrative design approach to achieve energy efficient design. And in this part, we also talk about something like a different, or not just in the design phase, but also in the construction phase and operation phase. What we typically do to enhance or achieve or ensure the building energy efficiency. So first we talk about the energy efficient building design. The key factors, the first thing for the reduced building energy load, we can consider all of the key factors of the building energy loads. So here we have a list of some key factors, like a building location, climate zones, air conditioned area, indoor design conditions, orientation, building height, all those are key factor. And the building envelope key factor like thermal mass, thermal conductivity of the envelope, solar heat gain coefficient, shading, and air tightness. There are also internal system load key factors like equipment efficiency and the schedules, occupancy schedule, ductwork, lighting power density, daylight integrations, controls, lighting controls, and the ventilation rate. All these are related to the building loads. One thing is the site, the design key factor, that's something like a more like from your environment, your location, and the building envelope, that's how the building exchange energy between the inside and your climate outside. And there are also internal things like your internal load, your equipment, your lighting, your people. So these are the key factors. We talk about each of them later. So the first, the design factor, climate, location, and site condition, such as temperature, solar radiation, wind, daylight, rain, site shading, etc. So for those kind of things are sometimes we can't make the change because when we have the location, then it will be something we can change. So, for example, the climate, solar radiation, most of things like that. So, based on my experience and as a previously as a consultant, we typically use a method called abundance thinking. For those we can't change, for example, because we typically think things like we focus on abundance or scarcity. By focusing on abundance or focusing on what the project already have for energy efficient design, will make we naturally get the solutions from the combinations of what is there. So that will make help to resolve the problem and see or find out more innovative solutions, rather than if we focus on the scarcity or what is missing, that will be really difficult to find a good solution. Here is a example of which is called the MADA Institute in United Arab Emirates. So this climate, next slide I'll show you. So in this project is located in a desert area, and so they have to be very creative with fighting the heat issues. So what they have or their abundance is like solar, lot of solar heat gain and a very dry temperature climate, and they really have a day and night temperature difference, very very big day and night temperature difference. So those are what they have as a abundance. So based on that, they designed specialized cooling method, like wind tower plus like night ventilation plus evaporative cooling. Just we will talk about a little bit later, just about this more, because they have a very dry temperature. They can use evaporative, and also they have a very big day and night temperature difference. So they can combine night purge and evaporative cooling, and so that's pretty effective for this location. And also because they have an abundance of solar, and so they try to shade the building, but also take advantage of that by like PV power, like photovoltaics to generate electricity. So that's an example to how to use the abundance methodology to for this climate, location, and the site condition factor. The next, it will be like orientation and mass affects the thermal loads and how buildings taking advantage of the location and the site related factors. For hot and humid climate, most part of the maybe certain part of Nigeria, the reduced heat gains to building interior through proper building orientation, shape, and the size, and the window and door placement will be very effective. Another design factor is the air conditioned area, indoor design conditions. That's determined like how would you condition the space, or would you like want it like be just naturally conditioned or naturally ventilated? Well, what temperature would you like to design the indoor condition? Is that higher or lower? If it's set, it's a higher, probably it will reduce your cooling energy use a little bit, or even maybe more. If they said it's lower, it probably use more energy, just something like that. Next one. So these after we those design factor, we'll talk about other things like for the envelope. Thermal conductivity of envelope is very important. So that affects how easily heat will flow through the envelope to the building, inside the building space. Typically, the design will prioritize continuous insulation and air barriers. So use continuous insulation rather than like the insulation is brick like in the segment. Eliminate or thermally isolate structures that extend from indoors to outdoors using low conductivity separation. So that minimize penetrations in the envelope between inside of the building to the outside. So that because that penetration will create a thermal bridge between the inside and outside. So for example, if outside is very cold and a lot of heat just loose from the inside of the building from this thermal bridge. So for the design, we try to minimize the thermal bridge by, if we have to have some thermal bridge because of some structure component, try to insulate that using low conductivity materials. And also the third design consideration will be specify materials with lower conductivity. That's to reduce the U value or of the building envelope. The next factor will be solar heat gain. So that's very important for both like a hot climate or cold climate. So which the solar heat gain coefficient, which is a fraction of the solar radiation emitted through the window, either transmitted directly and or absorbed, and the consequence release as heat inside our building. So when we look at solar heat gain, we mainly look at the solar heat gain through a window. If the solar heat gain coefficient is very high, then that means the window will emit a lot of heat into the building. So that is good for cold climate in the winter, but it's really not good for a hot climate, for example here. So minimize the reduce window size and reduce solar heat gain through the windows with shading and the glass with low solar heat gain coefficient factor will be very important for the design in the hot climate. Also, shading of windows and the building surface will reduce solar heat gain. That's obvious. And so, for example, in this design that we talk about, that the same example, the Master Institute, they create a lot of component that shade the window, and so they yeah, those but it still allows like ventilation or things like that. Next. Another parameter to consider is the for the envelope is air tightness. The air tightness is the degree of air leakage into and outside of the building's thermal enclosure. That is important for like cold climate. For example, in winter, they don't like the air to leak or go into the building. But it's also very important for hot and humid climate. Because for a hot and humid climate, the air both have like temperature is high and the humidity is also high. So controlled air and moisture infiltration and reduce heat gains can reduce heat gains. Include a tight building envelope for air-conditioned building in the hot and humid climate will be very important to reduce the air condition load. But if you want to design a more natural, like a naturally conditioned building, air tightness is not a factor to concern. This is only concern for the like building air conditioned building. For air tightness, we can test it with a commissioning the building envelope. For example, when you design it with a better air tightness, but in the practice, we probably want to test it to make sure. So you can test that. For example, this picture, they show that a blower door test to determine the air tightness of small buildings. That is typically used for small buildings. They use a fan and seal this wall, and then they blow this fan to extract the air from the room. And after the air of the inside is pressure is stable, they just calculate the fan flow rate. So they know because the air goes in through the building cracks will be equal to the air extracted through this fan. So they will know how the flow rate of the air infiltration, and they will calculate know and calculate the tightness status of the space. So I showed this slide just for the importance of commissioning of the building envelope. That we'll talk about that in the process, like outside the design process. That's in the operation process. That's also important for building energy efficiency, the building commissioning. So typically, the commission of the building envelope commissioning will likely will include like water infiltration, exhaust entrainment, thermal performance of building envelope, and the building envelope pressure, like building envelope air leakage, like this, and the daylight glare control. And people will choose some of the tests that really important for their building and performance. So they will test that. For example, when the building finish, they test if the envelope will perform as expected, as designed, or is there any issues like a leakage, or thermal performance, like for example, they will have a photo, infrared photo to test if the temperature difference of a roof or window, or some windows are really, they have a graph, and then if they show some temperature is high, very high or low, that probably indicate like a deficient of area that the installation has missed or something like that, or insulation is break there. So that's a envelope testing. Next. Another factor is thermal mass, which is the ability of the building to absorb, store, and release heat. For most common building materials, the higher thermal mass, the longer the thermal lag, providing inertia against the temperature functions. So thermal mass is like the materials that can absorb a lot of heat. And so when they absorb the heat, the building temperature will not rise very quickly. And then after it gets stable, and then if they can also release the heat slowly, and then the building temperature will not reduce very quick. So like shown in this chart, the green line is the external ambient temperature. So you can see with a heavy weight, which is just building with a thermal mass, the indoor temperature is most stable. And with a lightweight, with a building with not thermal mass, the indoor temperature has much more of like a variation. So that's how typically thermal mass is used. Thermal mass materials, typically they are like concrete blocks, tiles, brick, even water, and rammed earth and stone. So ideal thermal mass material will be like a high specific heat capacity and a high density, so it can absorb and store a significant amount of heat. And they have a reasonably good heat conductivity, so the heat has to be able to flow in and out. And the better has a darker surface, and helping it absorb and radiate heat. So next slide. Thermal mass for cooling, it would be very effective for hot and dry climate, which is a classical use of a thermal mass. Because hot and dry climate often they have a highly high diurnal temperature variation, so so that would make it effective. For example, if they have a temperature difference of 11 degree centigrade or more. And where nighttime temperature fall at least like 5.5 degrees below the desired indoor daytime temperature. Then at night, they use a cool night air to flush the heat from the space and cool the interior thermal mass. So after the whole night, the thermal mass is cooled. In the morning, next day, when the people come in, the space will then remain cool during the daytime without using any energy to cool the building. The more surface area or mass in the space, the more stable the indoor temperature will be. And then for that night ventilation, it would be good to use a cross or stack ventilation to cool the mass at night. So because cross or stack ventilation will likely to go deep inside of the building, so we will like cover as much as possible of the indoor space. If we use like a single side ventilation, that would be like they can only cover a little bit very shallow depths of the space, so that will not be very effective. It will be like a cross ventilation or a stack like at the top or the center of the building, something like that, to make sure that the air, cool air, just go as deep as possible. But for hot and humid climate, it will be very challenging to use this strategy, because the temperature difference is much less between the day and night. So it could be used maybe if you have can place it in a shaded area, but the effect will be much more compromised, just because of day or night temperature difference. So we already talked about the envelope, those factors that potentially affect the building loads and the energy use of the building. Another factors will be the internal and the system load factors. So one of the major factor will be lighting power density, lighting and the daylight controls. So lighting itself, it use energy. It's one based on in the U.S. data. It represents 17% of all the electricity consumed in the U.S. commercial building. So it's really a big one, making it the largest end use of the electricity in the U.S. Buildings. So that itself is a large electricity use, and also lighting is a source of cooling load for the building. So improvement and the energy efficiency of the lighting is very often pursued by building owners. It can both reduce the energy use of the lighting and also reduce the cooling loads of the building, and which may lead to our more cost-effective, less big capacity HVAC system. For example, use the LED lighting. The LED emits very little heat compared to other type of lighting fixtures. For incandescent bulbs release 90% of their heat into the building space. And the CFL compact fluorescent release about 80% of their energy as heat. So if you use a compact fluorescent, and 20% of the lighting power goes to the lighting illumination, and 80% go to the heat. So you have large less, and you have to use make a large lighting, design a large lighting power to meet your illumination requirement for the space. And then the large lighting power will release more heat to the space. And then you also need to a big HVAC system. So that's really not great for the building. So current trend is like a building use LEDs as much as possible. So you reduce both energy use of lighting and also reduce the heat. LED is much more expensive than the fluorescent bulbs, light bulbs, but it will last very long. The typical hours of LED is maybe at least 20,000 hours. It can reach like 50,000 hours, and they won't break. But the fluorescent, they can break very easily, and the life of the lamp is very bad, especially the compact fluorescent. They claim that the life is long, but it's really often it just stop working. So if you consider the life of the light bulbs, already the cost would be even probably not be that high compared to fluorescent bulbs. Just the initial cost is high, but in long run, the payback is definitely better. So reduction in lighting power density is a practical target that can yield substantial results. So in addition to the lighting, the lamp, the lighting type, the control of electric lighting, either by occupants or an automatic system, has the potential to significantly impact energy use. A typical wide use and already often used is an occupancy sensor that sense the for example, infrared sensor, and it's the most basic form of automatic lighting control. So it senses people inside the space, and if people leave, they will automatically turn off the lights. But if people go inside the space, and they just automatically turn on. So that can reduce the lighting use. And also the daylight harvesting and the automatic daylight controls saves energy and maintains visual comfort. That's people like daylight. So daylight is a really good one if they if well designed. It can both save energy and maintain comfort. And also there are some network control solution for lighting that can manage the entire floor of the building. That's more sophisticated controls. And that could be combined with other, like synchronized with other building system. For example, we have an occupancy sensor in an office space, and then if it control both lighting and for example, the HVAC terminals. And when people can go out, leave the space for lunch, for example, and then the light turns off, and also it sends a signal to the HVAC terminal, and that will likely, for example, it can reduce the temperature set points. So, for example, if it's in the heating mode, it's reduce temperature set points, or in cooling mode, it increase set points. So that will use less energy, or it reduce the supply air, or reduce the ventilation, something like that. So to reduce the energy. So that's a synchronized between systems for a more centralized control. So we talk about daylight harvesting. That people, as a lot of attending like architects, you are very familiar with this. So very good daylight design that would be very beneficial for energy efficiency and also the comfort and also interior effect like of the space, visual comfort. This picture shows a light shelf illuminated direct sunlight, so it also reduce glare and reflect reduce glare on critical task areas. And then they reflect the lights into the ceiling, white ceiling, so it has very high reflection ratio, and then they can bounce it back and evenly distribute that in deeper inside of the building of the space. The next load component will be the equipment. That is actually a very big one. It also just like lighting, it consumes energy and also adds heat to space. Typically, for example, our office building, they have a receptacles like computers and printers and like data, like servers and things like that, and other process equipment, like if a restaurant, they have like a cooking equipment, they will for receptacles, they will add a sensible heat gain, but for things like cooking equipment, they will also add latent heat gains like moisture or water vapor. They all need to be considered in the building design because they add loads to the space. So here the slide shows some typical receptacle power density of the typical type of buildings. So these are, for example, the assembly is pretty low, but you can see the healthcare building, they have a lot of equipment and have a higher receptacle load. And the office, they have probably dense computers and servers, then they have a higher a load of receptacle power. Here is also a list of like a restaurant typical schedule for internal load components. For lighting and receptacles, and it's like 80% or 90% for most of the hours that the restaurants are in operation. So these are a very big component of energy use also. So so we also need to consider about those plug loads or receptacles reductions and the controls. So typically, first we will eliminate unnecessary devices. That's obvious, and use the most energy efficient product. Because a lot of countries have those energy label for those building equipment or device or appliance. So we can select products with those labels. We can select the products with an endorsement type of label. For example, the Energy Star rated appliance. Or select a higher rated products with a comparative label. For example, the like this picture, the B level rated products in the EU energy label. So these typically the labels have two types. Like Energy Star is an endorsement label, so that means the label is awarded to products that is energy efficient. So just buy those products with the label, you will get energy efficient appliance or equipment, receptacle equipment. Or even Energy Star also label like HVC equipment. So choose those equipment will be very safe for like choose our efficient system, efficient equipment. And for a EU label, it's more like it's like a comparative label. It shows the different levels and the level of that product. So you can see that from A to G, and the label also shows the energy use per year of that equipment, and some typical parameters. For this one is likely for a refrigerator, so they shows probably the liters of volume of the refrigerators is something like that. So so you can pick one with a greener, the greener the better. So that's the second approach. The third is automatically turn it off or power it down when not in use. That could be like you use a occupancy sensor or scheduled operation of your receptacles. So you just turn off this like a circuit for that receptacles, like turn off the power from that circuit. So when at night they just turn it down. Another large source of process load reduction, if you have a data center or manufacturing project, there will be a huge energy savings if you apply the data center equipment efficiency equipment or innovate the efficiency of the manufacturer equipment. Do we want to pause here because we already reached 1 hour, or do we want to continue until the end of this section? Okay, I didn't see.
Hello, Ying, I think maybe if you can just finish this section and then run through the questions.
Okay, great. For the power reduction, actually, there is another new technology built to synchronize with the power grid. So it's a so the building automation system will be grid connected, and the power grid will control the reduce the real-time building energy use. So which is called a demand response. So the chart here shows the power grid example, for the power grid, for example, in the hot day in the summer, the power grid, everyone use a air conditioner, and which make the power grid has a very high demand. So the power grid will need like 80 megawatts, but they can only have 70 megawatts. They have power shortage, and probably will like shut down some of the things, and or they will have a problem. So then power grid will pay the consumer to reduce the the 10 megawatts to balance the supply and the demand. So they will send the building a signal. If you participated in the program, they will send you a signal and then to reduce. So if either you can manually reduce some of the, for example, you shut down on some equipment, or if you already programmed some that's equipment, some equipment can be shut down if we receive a signal. So that could be automatically shut down for a while. So that's something like a automatic reduction of equipment loads for a better operation. So that that will also benefit the energy cost of the building, because in the high demand situation, the electricity price will be like higher, because the electricity price is something dynamic. When the load demand is high, the price is higher. When demand is low, the price is lower. So people also think about like a strategy, like store the energy at night when the price is lower, and use it at day when the price is higher to save the energy bill. That's some other strategies to save the energy cost rather than the energy use, but definitely it's effective to save the cost. And another load is the ventilation load. Because all the air brings heating and or cooling loads, depending on the climate. Although air may provide free cooling, but they could cause a heating or cooling load. And the ventilation load in buildings means the primary energy consumption, the handling outdoor air, fresh air, to maintain the indoor thermal comfort. So that depends on the fresh air demand. That is the ventilation rate, and the indoor and outdoor air condition. For hot and climate, humid climate, the cooling load for outdoor air is high, because it's including both sensible and latent air. A latent heat gain. Sorry about that. So for a hot and humid climate, the ventilation load will be an important part. It's also an important load for cold climate. For buildings in the very mild condition, like for example, the marine climate, the mild climate, outdoor air is very good for free cooling. So they bring a lot of outdoor air to free cool inside of the building space. Some types of building or space need a very high outdoor air ventilation rate to remove contaminants, because they generate contaminants inside of the building. For example, the laboratories. So they bring very great heating and or cooling loads for the building. If it's located in a cold climate or hot and humid climate, the laboratory ventilation will dominate the indoor internal load of the building, and dominate the energy use of the building. So that will be a very big factor. So in laboratories, in the design, we don't care very much about the envelope, but we really care about how to handle the ventilation loads, for example, in the cold climate. And also another example is, that's, let me think. Yeah, just like a building with a ventilation loads high, other type. So that could be something that really make it a very dominant, important factor. So yeah, so probably we stop here, and because we will talk about step 2, this section is pretty big. So I will look at the question and answer questions. See if I assign the wind direction. Yes. Yes, the first step could be orientation building line with assigned. Yes. Is water an example of thermal mass material? Yes, it's not very typically used because it's another, you have to put a water tank, and that's a extra thing for the building, right? They take space. But if we typically we use like a concrete floors or concrete ceilings or concrete wall ceilings or something like that, it's naturally a building component, so it won't take space. But definitely water can be because of its specific heat is high. Next question. Come cross thermal modeling, passive design, increasing thermal mass to enhance heating, cooling, ventilation. It's a building and interior. Is this applicable in all zones? Oh yes, we talk about that. It's better for the space for the climate with a big temperature difference, and day and night. So it's good for a lot of climates, except for hot and humid that has a low temperature difference. It's also good for typical climate, like in the like a typical cold climate or colder climate, like here in the Seattle, or so. For example, they need heating, so they will have a thermal mass, and they have a big windows to get solar heat gain, and then they heat the thermal mass. The thermal mass store the heat, and at night it would just like release the heat, so reduce the heating load. So that's another typical use of the thermal mass. So yeah, it definitely used widely, but not good for hot and humid climate. The ability of slides is pretty for the study. I hope we can have a copy. Okay, yeah, definitely we will. I will send a copy and to you. I'll give you a copy. In climate response building design, how can we utilize high thermal mass through Nigeria? Southern part of the Nigeria is hot. It's hot. Yeah, looks like yeah, we will have the climate analysis in later in this section webinar. We look at the potential of thermal mass. I will that will show a chart for how many hours of thermal mass will be used. Probably the hot and dry portion of the Nigeria is probably in the north part, and that probably could be effective, but not very effective. My impression. We'll look at that. Yeah. Also, the use of building envelope insulation have proven to be very effective, but not utilized in energy. How do we convince clients about this energy efficiency? Yeah, we'll talk about that in the section. Later. So yeah, definitely we want, because it's hot, we don't need a very high insulation, but we need some insulation. We will talk about that, and also especially the roof. We need to insulate to make sure, because the solar heat gain from roof is very significant. So definitely need some a certain level of insulation, but we don't need like very high as possible, like a cold climate, because we also need to release the heat when outdoor air is a temperature is lower than the indoor, right? And the heat can go outside. So if it initially is too high, probably not good. Can we get the yes, same. Let me explain, please. Change material, phase change material. Related to thermal mass and the energy. I'm not sure what is the phase change materials. Maybe we can talk about that in discussion that at the end of this seminar, so we can talk that. I'm not familiar with this term. Following the three dimensions of sustainability in common, what are some of the indicators of these dimensions to see if a building is sustainable? Yeah, we'll talk about that. We have there are already a lot of sustainable design framework, and also they use that for certification. So they're widely available for like a framework. So you can just use that as your framework for the design that covers all these factors, or you can even certify your building with those framework. Great. Yeah. Maybe let's let's have a break for 10 minutes. We come back at 30, right? Is that okay? We come back. I don't know exactly what's the time of your location. So it's 30. I like come back at 30.
It's 2:20 here, so
Okay.
we'll take.
Okay.
So we'll come back in 5 minutes or 10 minutes.
Yeah, maybe 5 minutes. It looks like we have a lot. Hopefully we can finish everything in 5 minutes.
Okay, everyone, we'll take a 5-minute break, please. Then we'll continue. You can remain signed in, and we'll just resume in 5 minutes. Thank you. If you need to take a comfort break, or if you need to grab a snack or something like that, or step away and make a call, you have a missed call, you can use this opportunity.
Hello. Let's resume. Looks like because I have a lot of slides, so it looks like I need to speed up. So some of information I could probably skip some of the information. So yeah, let's start. So step 2 will be like optimize the efficiency of the systems. Typically, we'll think about the passive system, the common passive technologies like natural ventilation of the use of thermal mass, and also we'll definitely want to consider utilize this free energy, like exhaust air heat recovery, and also outside air economizer. This picture shows exhaust air heat recovery, which will recover the exhaust air from inside the building, and use that to reduce the, for example, it depends on your temperature. For example, if it's outside air is very hot and humid, and then you inside conditioned space, the temperature is low and the humidity is low, and then you use the inside exhaust air from inside to cool and dehumidify the incoming outside air. So that will be like using the free energy to condition outside, preconditioned outside air. So that's a very effective strategy, and also in the cold climate, it's also like it can use already much more warmer inside air to heat the cold outside air. So that's a very effective strategy to save the energy. Also, air economizer is something like when the outdoor condition is good, we want to cool the space, and when all the air is cool or cold, and then you can just directly use all the air to cool the build space inside. So net ventilation is something like similar to like outside economizer. Economizer can be used like in mild climate to cool the building. It's also cost effective. And then the efficient mechanical systems. One of the is the ground source heat pump. I don't go to very much detail because we don't have a certain time. So if you familiar with the air conditioning or mechanical cooling, so they will have a compressor and the evaporator and the condenser. So that is for they have they circulate the refrigerant. The evaporator will like when the refrigerant evaporate, pressure is low, and then they just evaporate because they need heat to change it from the liquid mode to the air mode. So they will absorb a lot of heat, and then the condenser mode, they will like press it back to the liquid mode, and then the heat goes out. So they just circulate this to like pump the heat inside or outside. So for ground source heat pump, the difference between air source and the ground source is because the ground has a much better thermal source because their temperature is more constant. It makes the system more efficient as a source. For example, in the cooling condition, the ground is even the air is temperature high, but the ground is low. And in the heating condition, the ground temperature is much higher than the outside. So that makes the temperature difference and the heat exchanger more efficient. So the ground heat pump typically has more better efficiency than the typical air source heat pump. And it can work both in the heating and the cooling mode. That's one of the efficient mechanical system. And also heat recovery. Heat recovery is always a good approach to in your design. So when you design the energy efficient building, definitely think about is that any heat we can recover to use it as free. So heat recovery chiller is one of the equipment that that use the heat of condensing. You can see from this chart. They use the heat from the air handler units that circulate the water, and when they go out of the air handler, temperature higher, and then that heat need to be, if traditionally they just go back to the chiller to and reject from the cooling tower, but for air heat climate recovery chiller, it use that heat, and then that's the heat pump basically, and they use that heat to heat the service water loop. So for like you can use hot water to use a shower or like a hot water sink, something like that. So that's a heat recovery chiller. And also another good one is the heat recovery variable refrigerant flow system, which is a good system, has a very good heating and cooling efficiency. They have a simultaneous. They can serve the zones like have a both. Some zones have heating and some zones have a cooling. So they, for example, in the perimeter zone, you want heating, and the internal zone want cooling. And in this case, they can recover some of the heat from the space from the system that reject the heat from the cooling, and use that heat for the heating the zone that needs heating. So that's how it is more efficient. It's typically has better efficiency than the typical air conditioner. Another one is a wearable air volume system. So that system uses a variable airflow at a constant temperature to heat and cool this building. So the flow will change, depends on the load. If load is higher, it will increase the flow, and the load is low, it decrease the flow. Because of the flow, you know, the temperature times the flow rate, you can get the capacity of the heat or the cooling capacity. So if the space need less heating and cooling, and then they would just request less flow. So several controls, also they can implement several control strategies like outside air economizer, again, temperatures supply temperature reset, static pressure reset. That will be good to reduce the fan energy use, and occupancy sensor based thermostat setbacks that we already talked about that, and the demand control ventilation, which is like if for example the space is a conference space, they will typically use a CO2 sensor. When the space is used, the CO2 level goes high because the space is densely occupied. And then in that case, it will increase the outdoor air to the space. And then after the meeting ends, people leave the space, and then the outdoor CO2 level decrease, and that the system will not provide all the air, or reduce the supply air to the space. So that will save the energy, which is called demand control ventilation. Another efficient system would be a district energy system, which is like if you in a big city, typically there is a central system The good side of this system, we will kind of look at the picture. This example of a city district system. So it's large, so it can apply a lot of strategies. Like, for example, they have a free cooling from the lake. They can apply renewable energy system, and like a capture with heat, and you have a solar thermal. They have everything, so that because the system is large, they can include everything. The district energy system has one or more central plant producing hot water, steam, and or chilled water for the nearby building. They typically use have like a central business district, college and university campus, or hospital and healthcare facilities, airports, military base, and the industrial complex. They will likely to have like a central, that's kind of central system to supply the energy or hot water, steam, even they have a generator to or zero water to supply all of these kind of energy to these buildings. The benefits will be like a lower building cost, a lower they save the building space. So you don't have need to have equipment like chillers, boilers, and because they graded diverse heating and cooling loads from a whole multiple buildings or even whole district, they will have a very stable combined load. So they will run in a very efficient, in the equipment efficient curve, that in a efficient condition rather than using a separate system. So they create an economics of a large scale. And also enable, just like we talked, the use of high efficiency technologies in that central system, such as a thermal storage. We talk about that, you can store energy at night and use it at day, so save the energy bill. And then combine the heat and the power, which I will talk about later, and deep lake cooling, that's free cooling, and the ground source heat pump kind of strategies. And they have a high reliability than your system in the building, and they have an energy like a resiliency, it's more reliable and easy for. And if you use a district system, you save a lot for building operation and maintenance cost. You don't need those kind of costs and people to do that. Another one efficient strategy for the district or campus or those central plants will be like combine the heat and power. They will include a generator in this central plant. So because generator, when they generate electricity, they will have it will generate a lot of thermal energy. So that typically they will be wasted because that's not used. But if they combine with the central plant, they will be used. For example, they can provide hot water, use that in the hot water, or you can use the heat to power the absorption chillers, so to provide chilled water for cooling. So this technology has few geographic limitations. I use a variety of fuels. And you can also include renewable energy in it. For example, you can use biomass to fuel the plant. Has been employed mostly in industrial, large commercial, and institutional applications. And about absorption chillers, we talk about that because it doesn't use electricity to compress the the compressor. So and can use other use heat produced in the electric generation process to provide chilled water. It's most cost-effective at sites that have a significant space conditioning requirements, like year-round cooling loads, like hospitals, hotels, large commercial buildings, a college campus. So for this chiller, instead of directly compressing the refrigerant vapor, they have like an absorbent fluid to chemically bond with the refrigerant vapor by changing the phase from the gas to liquid. So that's a different solution. So they just basically they just use the waste heat and make it cooling for free. Another thing. Okay, so we talk about the efficient system, and then we talk about the applied renewable. So we already reduce the load, use a more efficient system to reduce the energy use. And next step, we use renewable energy to further reduce the energy use. Reduce energy, the definition is like energy produced from the source like the sun and the wind that's naturally replenished and do not run out. So that is renewable. They can reduce carbon emissions of local environment benefits and reduce air pollution. And the renewable energy produced on-site project from energy price volatility and reliance on the grid. So that's a really great benefit by reducing the waste energy loss in transmission. And production contributes to reducing countries' demand for import energy. So so that's really good to reduce your demand and energy from the fossil fuel, and reduce your dependency for your the country depending on the energy. So the picture here shows a solar tower with a tower receive the focused sunlight. It's use an array of movable flat mirrors to focus the sun rays to the collector tower at the center. And they use a liquid sodium, which is used to store the energy before it's using to boil water or to drive the electric generator. So that's how another way to use like a solar energy in addition to the PV arrays. That is a solar tower. It typically used in a hot and dry climate, like arid locations. They has some drawbacks to consider, like they will kill birds if they fly in this array, because it's very strong light beam. The temperature can raise like 500 degrees. So it can instantly kill and liquefy the bird. So that's not liquefy, that's just burn and down. So yeah, so that's some concern, but it's really also effective for like those arid climates. Other renewable energy type as we typically know as solar, hydro, wind, tidal, geothermal, and biomass. That's all most typical renewable energy. I just have some notes for less used or less known renewable energy type, like a biomass. It is an organic matter that's typically a byproduct of a recently living and the plants and can be converted into a solid fuel. It's burned in order to produce electricity, which is still considered, which is not very clean, but it's because it's a additional byproduct, is still considered renewable and very cost effective. Also, the methane gas is typically produced through the anaerobic process during the natural decomposition of the organic matter. So it's occurs particularly in the bodies of water and the landfills. So those are like free renewables, free energy to use. And it can be produced at a particularly low cost, like both in the economical sense and the environmental sense. It involves the conversion of agricultural, domestic, and industrial byproducts that could be otherwise be wasted. So it's not that clean, but it's really cost effective and considered to reclaim the waste. So that's why it is still good. And geothermal is the energy that's harnessed from the heat that's being trapped underneath the Earth's crust. So that's not typically available. They only available some locations. It's available because it cannot. It's always there. Hydropower is very typically used, can generate electricity without emitting any greenhouse gases, but it also causes environmental concerns like damage wildlife habitat, harm the water quality, or something like the fish migration is obstructed. So for typically only low impact small hydropower is considered renewable energy. It's like a for example, the Green E renewable energy rating system. So they don't want like the large hydropower. Green renewables from new impoundments of water are not eligible. So they don't want to put the they don't. It's more like a stringent. They don't even want the hydropower in a new impoundment of water. But some other system they will certify as a even they consider less stringent for the hydropower. For renewable energy, we typically use is a photovoltaic, so called PV. So if you want to use that, it is a free tool to estimate energy use of this. It's available in this link here. It includes a lot of international locations, so you can include your locations here, and then they will and then include some your intended design of the array type and array size or something like that. They will give you an output of your energy savings from the your PV arrays. So it's pretty convenient too. It's online. It's free. For project, some project they have the budget to build a renewable energy system, but some project they do not build a renewable energy system by themselves. They can lease the system or partially own the community system, or sign a long-term contract to procure renewable energy. So there are a lot of ways to use the renewable energy in your project. So here, this picture is a solar farm. So organizations can probably lease a portion of the solar farm to or purchase a long-term energy use from the solar farm. That's to evolve the renewable energy. Another thing we will talk. We already talked about the design phase. Those how to make the building more efficient, and there are some very critical other steps and measures that's not in the design phase, but in the construction or operation phase to make sure your design is actually well implemented or effective. So that's one thing is the building system commissioning, which is critical to ensure efficient design is carried through to efficient building performance. The building system commissioning process is an integrated set of activities to ensure that the project meets both the design intent and the owner's operation needs. The value of a commissioning lies in its power to verify that those goals and objectives are met. Properly executed commissioning process often leading to like a fewer change of orders, a system and the fewer system deficiencies, reduced energy consumption, lower operating costs on the higher occupant health and comfort levels. So that's essentially just make your good design actually perform. So typically it will hire a qualified third-party commissioning authority to represent the owner's needs and to brought in the early design process. They will review your drawings and give your feedback, and then they will visit your in the construction phase. They will visit the site, they will test your equipment function and look at your like supervise the contractor's installation and test your equipment functions, and even they monitor your operation of the system. So that's just a third party to help your building performs well. They test your system. They can only they could do a monitor-based commissioning, or if you don't do a monitor-based commissioning, you want to monitor building performance. So that's another thing you probably want to consider in your operation, because you can't manage what you don't measure. So if you have the data, for example, your electricity monitor your lighting energy use and your HVAC energy use, and then you know why when it's higher, why the problem, why it's higher. Well, if you see some abnormal change, then is that something wrong? So if you manage on monitor, you can reduce energy use. That's I have a proof that if people building installing the metering system, and they will typically use reduce the energy use. So so that will like give you information how identify operation issues and save the energy. So here's a picture like if you installing different meters for different end use, and then that will go to a central software like a building monitoring system, and then that show the chart and to monitor the performance of the building. So that can and also you can analyze the data, because that record a lot of metering data, and so you can see the trend and even predict your building energy use in the future. So that's a very good thing to consider to install for operation. So yeah, that's the end of part 2. So let me check if we'll have any additional questions. You talk about light shelves. What are the likely material that can be used as light shelves in building? I think because it's installed on in the light like between the windows, like or on the high windows, it typically won't be like light materials because it won't be you won't use a very heavy material. They can use a metal to do. Typically, it would be like aluminum or something like that. So it's very easy to shape the surface of a shelf, and also it's light and easy to install with the metal frame. And also the reflectance of the material could be good. Definitely metal would be, or some plastic, probably also good. But the concrete, I think that's too heavy for, definitely too heavy for that. But probably you have a very good surface because light shelf, we want to reflect that light. So if the surface reflection is not good, that won't be a good for light shelf. The best it will be the metal or like a very high light, high color, light color, like the plastic, something like that. Okay. Energy efficiency with the aesthetic of architecture, what activity define this dependency? The name of the question is to between the energy efficiency and yeah, that's a good question for considered by the architects. So that we'll talk about that in the integrative design process. So definitely want to, because oftentimes they will come from the engineers, and then the architects will also have their consideration. So they will need to sit together to discuss that, to make it looks better, looks good, and also effective. Definitely that's something to do in the design. What is most effective way to enhance people awareness to energy consumption? Yeah, the most effective way to I think the monitoring will be one. If they are the owner, they will use the energy bill, right? They know how much they spend. But if they just are occupants, they need education or display. In many buildings, they display the energy use, like they have a monitoring interface. They just put at their office space, like a screen, and then they real time they show their energy use, or maybe they already combine that with like a temperature and CO2 level or indoor measurement of other chemicals, and so that display will is typically used to show the occupants to be awareness of the aware the energy consumption. There are also something like I know the lead like a rating system. They will give you some like a performance based rating system. That if you're certified, they will give you a dynamic plaque. That's is a instrument like you install like in your building that's dynamically show your score of energy and water use scores. So that's something show that I think that would be good way to show that. Okay, let's start the next part. Which is energy efficient building design process. So So we talk about the integrative design process. That's typically used by and energy efficient building design and sustainable building design. So in that design phase, especially at the beginning of the design phase, we use that as approach. That approach typically include the climatic analysis and the energy modeling analysis, which is a simple box. It's not like a very detailed analysis. And other analysis based on the team's goals, like related to energy, for example, like daylight analysis. Or some natural ventilation analysis that related to energy. That is often used by the integrative design approach. So it is considered with the design method like reduce load and utilizes efficiency of system. So it mixes with those two steps. This method is like a beginning the pre-design includes a team of multi-stakeholders and disciplines, such as the owner, the architect, and if you maybe you have a consultant of green buildings, and engineers, tenants, and our community members to work together seamlessly to identify opportunities to achieve synergies across the disciplines and the building system, inform the design and each other's decisions. The benefit definitely will be like a full alignment on the requirements, opportunities, and constraints among the disciplines. So so everyone will be well informed of everything at the very beginning of the design, and they talk to each other, and so they have a synchronize and leading to better design decisions. So the importance of the integrated design starting from the early age of the project. So that chart shows a typical situation that at the cost of design changes will be very high at the end of the construction, in the construction phase, but very low at the early design phase. The ability to impact the cost and the functionality of the building will be very high at the early phase, but very low at the later phase, especially on the construction phase. So if something goes wrong at the design, the cost will be very high to change or even unable to change at the end of like later phase in the construction. So even a very small change will have will be quite expensive. So the intent of integrated design starting from the early stage, so that will be move the curve, like red curve, the traditional design process that put most energy and effort in the like design development and construction document to the preliminary and the schematic design to make sure everything is good, and then do a more analysis, and then that will reduce your errors, like wrong decisions of design that cannot be changed later. For energy efficiency design, the integrative approach often needs to perform climate analysis that we already talked about that. And so in that process, we'll think about strategies by question default assumptions or universal design. So think about more innovative or project specific that were customized to the project approaches. And so for climate analysis that need like hourly climate data. The data are typically typical meteorological year data, which is not a single year. but probably like at least 12 years. That's so that can represent the typical weather information. So for Nigeria, you can download. We put the source linked here for free. So there you can download, if you're interested, you can download those locations of your annual climate data for your analysis. For Nigeria, you can ignore the climate zone because they are defined in different system like standards, but it just I just use ASHRAE, which is the American Society of Heating and Air Conditioning Society. So they define the climate zones. I use that, and in Nigeria there are some hot and humid climate zones, and extremely hot, dry, and those are in the gray area north, and some extremely hot and humid, that's a white area, and the very hot and dry, that's a pink area, and the and some hot and humid red area zones. Oh, this is not pink. Actually, the purple areas, most area is hot and humid. Sorry about that. The pink area is here. It's a very small area of a hot, very hot, hot and dry. So these are list of these climates, like the savanna climate, semi-arid, hot and semi-arid. So these are typical examples. So like the capital Abuja and as of savanna climate, you guys are more familiar than me. So these are the information that plotted on the chart that you can see on the less temperature swing. Oh, that's for Kano dry, and this is tropical and more rainfall. And this one is much drier and have more temperature difference. So we go to the climate consultant tool. So that's for climate analysis that typically it can be used at the beginning of the schematic design by architect. It's a simple tool to use with when you have the climate data. You just use that, import that into the data and show that they can plot the data and organize and represent this climate data in easy to understand ways, and help users create more energy efficient buildings. So they show with this data, and they will show the strategies that is potentially effective for you consider, and the percentage of hours that the strategy is likely effective. So I've shown example for Abuja. So that's the climate consultant shows the temperature, average temperature, and that's a solar radiation information for the whole year. And this is the sky coverage that shows like a lot of sky coverage in the from May to August. And this is a temperature and the humidity. So it looks like humidity is pretty high, and in most of the a lot of seasons months, but this could be low in summer because it's like a savanna climate, and also the temperatures lower at night but much higher in the day. So in the daytime it could be 30 or 40 degrees. So that chart shows the strategy that could be effective. So you can see the most like 48%, almost half of the hours that's falling the cooling and the dehumidification that typically need our air conditioner. That's in the right side of right higher side of this chart. Because yeah, I just explained the chart. The chart shows the dimension is the lower bottom is the temperature, and the curve are the relative humidity. So here is 100% relative humidity. Here is 90. So that's so if here for the dots here that have a high temperature and also high humidity, that's a hot and humid. So most of the hours are just all here. So they are like 20 degree to 30 degree, but the humidity is pretty high. There is a comfort zone here from 20 to 25. That's that area is the comfort zone. So it shows like a very small amount of the hours falling this comfort zone. In addition to that, there will be 30% will use sun shading of windows. That will be effective like more than 2,600 hours. And then that will be and then will be like a dehumidification only. And then that will be two-stage evaporative cooling. We will talk about that later. And the fan-forced ventilation cooling. So you can see that other things like high thermal mass night ventilation have 0 hours. Internal natural ventilation 0 hours. Other things like just for heating is definitely not applicable. So these are some automatically the software give you the suggestions, like but they are just automatically generated. You can consider that they could be effective, but you need to be more evaluated more. Another thing I want to mention that this oh no, sorry. Want to consider is a oh, I skipped one slide. I'm going to go back. One thing to consider, this software is to for small buildings because they consider the envelope gain, heat gain or cooling gain is a dominant for the building load. So that's more like a related to the outdoor environment. But if you have a building that's really have a lot of inside space, that will be different. So that if for a building is really huge, have a lot of inside space, and so this analysis will only be applicable for your perimeter zones, but not your internal zones. If you have a very big and multiple floor building, the internals, because they don't have a heat exchange with the outside of building, so the cooling will dominate the inside of building. So they will not, these analysis will not be applicable. This chart also shows the adaptive comfort natural ventilation. So the natural ventilation we talked about in the past, slides before is for the it's not for the adaptive. Adaptive is like considering people more like change their clothes and then change also you like to use fans and or more psychology adaptive because they have a natural ventilation, so they go extend their comfort zone. And so that with that adaptive model, it typically like range from if outdoor air is 30 degree and indoor, you can adapt. People will probably tolerate even the indoor temperature is close to 30 degree, rather than just in the comfort zone like 25 below. So so if with that adaptive, about like 44% will be in that region. But this is 40% of hours. They could be like a lot of hours is in the night. So that's something we could consider. We will think about it. For example, if you have a office building, they're probably not good for use this setup because people always work in the daytime. But if you have a more residential or building running 24 hours, that could be something to consider. And here's another example of a volcano, more solar radiation, less like a heat coverage of a sky, the humidity. Oh, there are some dry. You can see the dry humidity, like humidity lower in the day, but temperature is also high. Sometimes, yeah, it reaches 40 degrees at the day. So this climate is a bit different. You can see the chart that shows part of the hours is half of them is in the hot and humid area, and but a lot of it is in the hot and dry, because the humidity curve you can see that's pretty low. The temperature is high, but it has more hours in the cooling, in the heating condition, even below 20. It's not much heating, but it's definitely much lower and much lower temperature. So the suggestions like definitely less hours no need cooling and mechanical cooling. They have a two. The second is sun shading. That's still good, and then another one is a two-stage evaporative cooling, because of you have a dry and hot hours. And next we passive solar. That's for those hours that could be used for this area. So for the adaptive model, they will be like still something 30%. So that we'll go to the energy efficient design for hot humid climate will be because it could be a very challenge. They have a extremely comfort problems and the potential for condensation, mold. And so the strategy would be like a minimize building cooling load. Cooling loads typically come from heat gain through the envelope, lighting, receptacles, scorpions, and ventilation and infiltration. For envelope, you consider massing and orientation and envelope insulation. For wall and window insulation, will be appropriate. In this climate, more window wall insulation may increase cooling energy usage and result in less energy savings. But because of the building envelope insulation in hot climate may trap heat inside the building. In this cooling, when outdoor and temperature is lower at night, won't help to release the heat to the space to outside, but they still need some insulation. In the hot days to prevent heat to go inside the building. So the insulation don't need to be very high. It's just some certain level. And the for roof insulation, we need, because sine angles is very high, and then sequential larger solar gains from the roof than the wall. So roofs are more vulnerable to the solar heat gain. Increase roof insulation and the roof reflection. They can use a very bright roof materials, and also probably consider including like a reflection film, like to in the roof layer, something like that. The window shading and the window type, that's definitely reduce solar heat gain for the building. And then also consider interior lighting reduction to use most like LED lamps, daylight controls to reduce the heat from lighting, and also reduce the equipment load to reduce heat from the equipment. And for building systems, you can consider like a high efficiency chillers, AC, and the VRF, variable refrigerant flow system, and consider to use air-to-air heat recovery unit, especially the enthalpy heat recovery unit that's recover both sensible and latent heat. So the humidity, you can also recover that. And the dedicated outdoor air system, which is very good for that location. And install renewable energy system, and then a combination of above the two systems. So you can use a dedicated outdoor air system and with a heat recovery. So you have a outdoor air come and then use the exhaust air to cool the outdoor air, and in that system. So that has been approved very effective for hot and humid climates, and save that called a decoupled like a humidity control, and because that leaves your other system only handle the sensible cooling load, but leave the outdoor air system to handle the humidity. So that make your it's more effective, more energy efficient, and also make more process to control your thermal comfort and the indoor air quality. And then that's the last thing to consider, use renewables like PV panels and a solar hot water system for your domestic hot water use. Yeah, we will talk about the cooling loads, like sensible and latent. So by conditioning outdoor air and return air into separate, that's called decoupled. That will be very good for control your the humidity, and good for comfort, and good for energy use. So yeah, it's a good use that to combine with enthalpy wheel heat recovery. For hot and dry climate, most efficient strategy are similar to hot and humid climate zones, except the HVAC systems. Or not just except for hot and dry, we probably may use the thermal mass, but the hot and humid is not a good choice. Air to the HV system, like an air-to-air heat recovery unit, and these are the same. And the other two additional things could be considered like a radiant cooling system, this is not good for humid climate, because if you have a radiant cooling, that you're running the cooling water inside of a radiant panel, that could cause condensation for hot for humid climate. But it will be very good for hot and dry climate. And also the evaporative cooling system is not good for hot humid climate, because the humidity is already low. You can still evaporate, but it's if it's higher than 80%, that would be not very much effective, or the capacity will be much less. So that could for hot and dry climate, you can use directly evaporative cooling system. So that's in the here. So you just have a water run through this, and the warm air go through the water, and then they evaporate. When the water evaporates, it take the absorb the heat, and then so that your temperature, the dry bulb temperature will reduce, the air become cold, and then the heat and that kind of energy goes into the moisture or the humidity of the air. So the air gets more humid, but the temperature definitely gets definitely much colder. So it could go into the comfort zone. And there are also indirect evaporative cooling. So air goes through this inside like a device, and evaporative cooling just occur outside. So the air is cooled there, it won't absorb the humidity of the the water from that evaporated. So if you want to maximize the effect, you can combine the indirect and the direct evaporative cooling. You can first run the indirect evaporative cooling. So the air is cooled, but it won't get the humidity, right? And then run the air further to the direct evaporative cooling too. So it's reduce the temperature further, but get more moisture. So the temperature will be reduced from step 1 to step 2. So that's the two evaporative cooling. Stage 2 is also called 2-stage. Here is the example we call we use like for the Mazda Institute, and we talk about that they have a wind tower, night purge plus evaporative cooling. So they have conducted like in-depth environment analysis in the early design phase, including solid studies, wind tunnels testing, and energy simulation. So every design of the architectural design, they actually is not like just architects for like how like purposes looks good, but actually all these are combined with analysis of energy and like performance. So all the shape is not like has determined based on this analysis. So like from this chart, you see that air is drawn from the tower, and then that's hot and dry, and then there is a mixed jets, the jet water, and then the air gets cooled and goes down and supplied to the people. So that wind tower gets capture the wind, so they will get to ventilate the space. So you can see with the evaporative cooling, the temperature goes down a lot, and from the chart above, you can see a lot of hours is in the right side with the temperature high, but the humidity like relatively low, and then with evaporative cooling, those right corner, and they go back to the comfort zone, but even the temp or a little bit above, so the temperature gets lower. The some of the humidity, because it was dry, so even the humidity increase could be still okay. So that's how it works. It works. Oh yeah. So that's the analysis. So there is a design concept design report for this building. I just include the link in this slide, so you can look at that after this seminar. It includes a very good detailed analysis for this project. It's I think it's done by Norman Foster architects. So it did a really good analysis. So I think you recommend you look at that. Another thing is a simple box energy model. A simple building form. So you can in the early design phase, you just quickly build a box, and then box model for a building. So and quickly apply the considerations to see the results very quickly. So for example, in the prelim concept design, you can just create this rectangle thing. And in schematic design, you can further analyze that to use a more accurate design. And so this energy model you can use throughout your design phase. So it can give you feedback for at the beginning of a big picture thing, and or you can analyze very small things. You can even use that. There is a software, probably you already know, that eQuest, which is free for download, and just show this picture here. So it's very easy to use software for, especially it can use it for schematic design or for very detailed energy modeling. So it's very widely used. It's free, so you can probably consider use that in your design stage. For example, you can analyze your building shape, your window to wall ratio and skylights, and shading device, see how they impact the energy use. It could be very easy to operate in the software. And it's good for architect. So even you're not an energy modeler, you still will be able to learn it very quickly. The interface is friendly. Potential strategies using simple box models would be like site conditions, land, like solar, like a mass orientation and natural ventilation and basic envelope attributes. We already talk about that. Lighting levels, everything here you can analyze everything related to energy and but for the beginning of the phase, probably focus on most important things like this. So we already talked about that. So if you do energy model analysis, it should be an iterative process. So when you in the later, at the beginning, it could be like a very simple shoebox, but later it need to be more accurate. So the model process will be like a iterative process to inform the design with results carefully checked especially in the middle, like when you really want to analyze something that's more detailed or in detailed comparison. So still need some skills, like for example, if the input is not good, and then the output will be not reliable. Other related analysis, like thermal comfort, because that's highly related to energy use. There is a comfort tool can use. that's free online tool to see if your design is comfort or not. And there are daylight modeling, and if you want apply engineer natural ventilation, the safety modeling that could some consider, but this one could be expensive because there are no free tool for that. At least unless you develop that, it's very complicated. So that's our section part 3. Let me check for energy efficient building design process. Let me check if any further questions. Positioning of walls insulation. Oh, yes, here. Is the is those things in slides can help us get all the weather analysis of Buja? Yes, definitely. Weather analysis, that software is could it's good for like a temperature kind and it also has wind. I didn't show it. It also it has a sky cover radiation. Yeah, it covered almost everything. You can because everything in the weather data you can actually plot on the software. And after you download, it's free to get. You can search it up. It's free, so I probably didn't include the slides in the slides. You can search it. It's easy to find. You just type climate consultant software. You can find it. Positioning of wall insulation is important. Yes. External insulation will also trap heat because if you attach to the wall, it will also trap the heat. The location of so if you attach outside the wall or inside the wall, for heat it doesn't make much difference. It could be make difference for like condensation where if condensation occurs, is that occur inside or outside or some, that could be something you want to consider. But for insulation for heat is probably is very similar. We can you can probably consider that analyze that further. The only concern I think is the condensation. What is air-to-air heat recovery unit? Yes, that's we just talked about that. It's air. The first air is the exhaust air. Another air is outdoor air. So you exhaust air out and outdoor air goes in. So you recover the energy from the exhaust air. The exchange actually is exchange. For example, the indoor air is colder and drier because it's a condition, and out there is hot and more moisture. And then when the units just exchange their conditions, the heat exchange make the outdoor air drier and colder. So that precondition your outdoor air into the space without additional energy except for fans. So so that's the unit. Okay, next let's see if we probably need some 7. Yeah, so we have through the times, right? It's at 3:30. It's at 3:39, right, at your location. Yeah, probably we can have another break, a 5 minutes break, and come back. We will come
all right.
back like, yeah, at 3:45.
And that sounds good.
All right. Thank you, Ying. Thank you, Ying.
Yes, Emmanuel, you were saying.
Just thank you to her. I was just thanking her.
Okay, so let's take 5 minutes, please.
Hello. Yeah, we just got another question about eQuest and the AES-VE software, which is better. AES-VE is a software that's has a charge, so it definitely has a better function of they have a support team, and because it's not a free, so they have a support team, and they have a more function like a combined analysis. I remember they probably have a like a natural ventilation and a daylight analysis. It's definitely this is better than eQuest. eQuest, because it's a free software, they don't have any team to like support the user, and also their development like a version update is very slow. So if you have a budget, you can consider the AES-VE and other software that's like a more they have more function and they have a support. If you have a question, you can have people to ask. And eQuest listed here just because it's free and easy, and also easy to use. So it's still a lot used a lot by people like designers and project team. Yeah, I think they depends on your budget. And also, I think probably eQuest is like easier to use than AES, but AES has more function, definitely. Okay, let's start the part 4 case study. We have just a note that I found some there are cases in the lead certified project, because we have the data. We have a lot of data for lead project, but we can't release that to use as a for like a educational or like for other publications. So these two are the two I picked just from that's published by the USGBC, so they already acknowledged the project team acknowledged to publish that. So I use that for the example. And I'll use another one that's from the published website. So we, as a certification body, we unable to release more information. So that's a limit our ability to share the information. So this is an example with this Olympic house in Switzerland. Which is a LEED version 4 building B, D, and C platinum rating. The building facts is it's like a 25,000 square meters. They have a 3 ground plus 3 office floors and a roof terrace here. And they opened in 2019. These are the number of occupants. It's a medium-sized office. You can see from the picture they have a lot of PVs and a central atrium with skylights, and they have a very well designed envelope and a good like a landscape design. And their climate zone is based on ASHRAE is a climate zone 4A, which is relatively colder and humid in the summer. So they did the integrated design analysis, consider the interdependencies. So they bring together people of different expertise to design the best new quarter they want. So for that, in the different factors, they separate them as a design, the building design, the energy efficiency, and the comfort. They consider those three dimensions, and inside of that, the energy efficiency, they overlap different factors. For example, the energy efficiency will they cover all acceptable acoustic, and the factors affect all of these two or related of these three are like a building facade, artificial light, daylight, thermal comfort, and climate concept. And the building orientation will be like between the design and energy efficiency, but it doesn't very directly relate to comfort. For energy and the comfort, ventilation and the location, that could be like important. So they analyze all of these in the early design phase with the integrative process. So here I just show some information of the this analysis. So they have that's the chart of the whole year temperature, all the air temperature data. So you can see there are lots are in the natural ventilation zone between the it is like they determine is from 10 degree to like maybe 26 or 27 degree, and then they analyze the wind and the temperature. So you can see the wind most come from the northwest, southwest, and the northeast direction, and most of the winds are like between 0 to 3 meter per second, and some are higher here. So the blue area is like between 0 to 3. That's the majority of the condition. And for the temperature data, similar will be analyzed, show the with the climate consultant. They show that these are with this area is the comfort zone, and then a lot of area you can see that like temperature is lower than the comfort zone, so that means they need the heating. So that this location is heating dominated. Just a very small amount they need cooling, so they are a little bit hot and drier. Humid, like relative humidity isn't very high. It's like summer is a bit above the comfort level, but not too high. So they did the integrative design analysis with a simple box model and other analysis tools. They analyzed some these things we talked about before, site conditions. So that shows the initial condition or consideration, and that part is the what they analyze, what is their decision. So for site condition, the building is located on the site near the lake. They have a district heating and cooling system available as HVAC options. So they consider heat pump rather than district heating, because that's just a decision. They feel the heat pump may be more interesting or long-term investment. And then they have a lake, so they think they probably use the lake as a free cooling strategy rather than the district cooling, because it's more free and more sustainable energy source. For massing and orientation, it is a compact building to reduce the footprint. And the roof, they maximize the renewable energy. So that's the same in the process. For building envelopes, their intent is to maximize outstanding beauty, but also promoting well-being. So they analyze annual system. They consider different annual system. It's compared, especially data within the double skin facade. They analyze 3 options, and finalize. They find one option which is balustrade with vertical gas solution for the double skin facade to limit solid gain and better thermal comfort and reduce energy consumption. For lighting levels, they want to use they want to enhance comfort by providing optimal lighting control. So they considered a task area concept. So different fixtures are installed for the occupants to adapt lighting levels to their task, to allow more flexibility and improve user comfort. For this building, they consider comfort more than the energy. They also consider energy. So they put a task lighting at all the office desk, and use a light ceiling tiles to reflect, to have a better reflection. So that reduce the total lighting power, and also the people can turn on lights where they need. So, and the task lights is more comfort than the like general lighting, and they use full complete LED lighting, so be more efficient. For thermal comfort, they consider the air conditioning system to compare for better comfort. They compare some active baffle system and also active slab, which is a concrete slab, active slab. That means they running air conditioning inside the slab, so they call it active slab. And they have also suspended chill ceiling strategy. So they finally decide use that one because the baffle system will block daylight. It won't. Then it will be discarded. And the uncovered ceiling slab, concrete slab, is not good for install other sprinkler and ventilation ducts. And suspended chill ceiling strategy is good, and so they run the chill water through the ceiling to reduce the to cool the space. So that will eliminate the ducts to reduce the ceiling height, and that also combined like consider together with the lighting design and with like architectural effect. For operation consideration, they will consist smart buildings, flexibility, mobility to improve workforce comfort, control lighting by a presence-dependent system. So that's a occupancy sensor basically, and the daylight simulation results used to analyze the facade design, size and position of office along the facade, and enhance the use of a naturalized in the space. So here is the analysis. They analyze the facade and the design. So they consider the noise, natural ventilation, daylight, and the solar gain for that design. For noise, because there is a highway on the noise, so the noise facade is designed as a double skin to block the noise. For the east-west facade, they think probably better, so they just use a single skin envelope with natural ventilation element, because for the wind rolls, you see that the ventilation is like a wind, prevailing wind is go this direction, so they will take advantage more of natural ventilation here. So they for natural ventilation, they will do that for all the like parameter zones. For natural ventilation, there is an issue to consider is the draft, because they want to use like a use that, but sometimes the wind speed is high. So to reduce the draft, they need to they consider double skin facade. In the north and the south, they have this for double to reduce the draft, and for the east west, it goes it's a single skin. They consider some elements to reduce wind pressure and allow the controllable air infiltration. They like face the yeah, it doesn't show exactly how they reduce the draft of here. So that's basically how they consider. So for daylight, so that to make the daylight, you can see from the photo that most of the building has a like a glass envelope, so it's to maximize daylight effect. For solar gain, they want to reduce the solar heat gain. To control it, they have a external shading device outside the facade, and they also consider the internal shading device inside the double skin. So so shading device will be best to put outside the window, because it shades the window, and so the heat will not go inside the window. So if you put the shading device inside of the window, like blinds, the heat already goes in. So it actually it won't help very much. But it will help, but it won't. But the heat is still goes inside, already goes inside. So consider external shading device. So for double skin, they put it inside. It's because it is still have an inner skin there, so they can control solar gain inside the double skin. So they can another analysis that they can talk about in the previous slides. They can have a compare 3 facade design for the double envelope, and so the first type 1 is like a reclined, like a glass with a shading overhang here. The depth of the envelope is less, probably because it's not vertical, and the type 2 that's vertical, and the similar position of the shade overhang. And the type 3, that's finally they used. They have a partial window in the inside layer that reduce heat gain, but they maximize daylight by push the overhang above. So you can see the greater area inside of the space and use the daylight. So they simulate and get energy use. So you can see that facade 1 has has more cooling, both heating and cooling energy use. But facade 2 is close to facade 3, but facade 3 is the best one. I guess for facade one, because why it has more heating and cooling and they use most of the heating, probably because it has more envelope area actually, because it's not vertical. So they also analyze the 3 facades with daylight effect. So both energy and the daylight is an important thing they want to consider. They use a factor parameter called daylight autonomy as a point in the building. So for that means the percentage of hours, occupied hours, when the minimal illuminance level can be maintained by the daylight alone. So for example, for office, if you want to use like 50, this building is designed with high luminance level, like 50, sorry, 500 lux of 50-foot candle. So so they just how many percent of hours occupied that like this level of luminance can be reached in the whole year. So they modify this, use the continuous daylight autonomy, which is consider some of the hours. For example, if the level threshold is 500 lux, but for the hours like 400 lux, and they still consider as a 0.8 because sometimes people still tolerate 400. For office, like 300 to 500 is a typical range that people always like 300 people. A lot of people are always good for 300 lux, so they consider that and do some simulation and find that still the facade 3 has a better continuous daylight autonomy. So so both for energy and the daylight, it is better than the other options. For ventilation, the concept is major concept because the building is a size is like a shape is big and like it's not narrow and long. So it's the inside still they need to use mechanical ventilation, but they do consider natural ventilation at the perimeter zones. So this they designed the perimeter area can be shut off while the internal central rooms will be supplied by mechanical with fresh air. So when they calculated the loads, the mechanical, they only consider the internal zones for the mechanical loads. So that will reduce the energy use partially for mechanical cooling and ventilation. They also use a very good insulation in this building for envelope because they are heating dominated condition climate. They use a dedicated auto air system with exhaust air heat recovery. We'll just talk about that in previous slides. It's very effective to pre-cool or preheat the auto air, and also better for comfort and ventilation. And they use LED lighting and the water from the nearby Lake Geneva to cool the building. And then they apply the renewable energy on the roof. So this picture shows that they pump the water from the lake. The lake water is always like 60 to 8 degrees. That's perfect for cooling. So they use that for free, just more some pump energy. So that chart shows the energy use of the building before they apply the renewable energy on the top of the roof. So you can see the major reduction is in the space heating category, which is the green. So almost like a 90% reduction. They have a very good envelope and plus heat recovery and efficient HVAC system, and somewhat reduction of the lighting, because this is a LEED certified project. Just a note for that. The baseline is based on the LEED required baseline, which is ASHRAE standard. That for this version, they require daylight controls and occupancy sensor controls in most of the space. If they available for, like, for example, you have a big space of with windows, that baseline requires daylight control. So for this building, they with daylight control, they won't get much savings from the baseline for that controls. And also because they designed the interior lighting as a 500 lux, which is good, and they want a better lighting effect, like comfort. So that probably why they don't reduce the lighting power. Even they use LED, lighting power density is probably not very low, because a lot of other buildings use 300 lux. So that's why they didn't reduce that a lot. But you can see for cooling for this project, is even they use this free cooling. The cooling, it's almost gone for the proposed. Yeah, it's gone for the proposed case because they use free cooling for entire building. But in the baseline, even they don't use that, because the climate is a very small portion of the energy use. And another is the fan. They use they reduce the fan energy. Reduce heating and cooling, that also reduce fan energy automatically. And a lot portion is receptacle loads and process. That's something it didn't do much reduction. It didn't reduce it. So that's the picture of this building, and they applied a lot of renewable energy. So the final energy reduction would be much lower than this, and it could be much probably here and here. So that's the first building, which is a very highly rated LEED certified building. Another one is also a platinum rating LEED building with a version 3, which is a previous version, which is this building is opened a few years ago. It is located in a different type of site. It's an urban tight site. So you can see it's just the site is just about the same size of the building, and it has 7 stories. It's also located it's in Washington D.C. It's also like a similar climate of the the one in the of another example. So for this one, I just this building is not like from architectural design, is not that beautifully like a design. It's just a example, like they use a lot of like we tried very hard for the strategies used to reduce energy use. And also they use integrative design practice. Even in the version LEED, an early version, they don't really need required to do that. This building established like open channels for communications between stakeholders, and achieving the pre-design throughout the design phase, identifying unique opportunities that is synergies across disciplines. And a unique thing that's involved the city authorities early in the process. I don't know. I probably because they want to take advantage of this city water system. They allow the team to work out the logistics and requirements, which merging technology to get energies from savings from this over the solar system. And so so this project they have a very limited site, so they cannot apply like a efficient system like ground source heat pump, but they still want to consider similar strategy like ground source heat pump. They want to just extract the energy from the solar system. The solar, because the solar line runs in front of the building. Additional reduction strategy is like high performing building envelope, natural daylighting, building energy efficient building control system, LED lighting, reduce the plug loads, radiant cooling system, dedicated outdoor air system with exhaust heat recovery. So we already talked about that. And radiant cooling, we talked about that. It's not very good for very humid climate, but this climate is fine. They very control the humid good, and the wastewater heat recovery. So here, oh, I cannot show the, oh, here it comes. So I just show the video that's from the published video that's from YouTube. So that introduce that is the system. That a picture shows the in the construction how they handle that system to install a heat exchanger. Oh, can you hear any sound from here? Probably not, right? I'm not sure.
No sound.
Oh, yeah, that's a problem. Yeah, I didn't consider that. How to make? Probably I will just remove my I'll try again. Can you hear the sound?
No sound yet.
Can you hear the sound? Hello?
Hello.
Hello? Can you hear the sound when I play that that video?
No sound yet.
Still no sound.
Oh yeah, that I don't know how to make it happen.
Maybe just tell us what the video is saying.
Yeah, they just say they use that system. They just want to share more information, but basically they just use this solar exchanger system. So they because a lot of water runs through it, the water temperature is low, and then they use like a water source like they exchange heat like for like a heat pump. They use a heat pump to attach to it, so they extract the heat from this water flow. So they make use it. for the building to cool to cool the building. So basically, that's just that strategy. Well, I apologize about that. I didn't I don't know how, because I'm not very familiar with how to use this Zoom. So yeah, probably we just skip this one. So and so this chart shows their energy savings before applying the PVs. So they reduce a lot of heating by insulation and it also the heat recovery. They reduce a lot of cooling with some that strategy, and fans. They also reduce actually even the receptor equipment is a model the same in the proposed like a baseline building and the building and under the building. Actually, they implement strategies to reduce the receptor equipment. So you can see compared to the last building, that building receptor equipment energy use is much more. It's kind of as a percentage of whole building energy use, but this one is much less. They reduce the receptor load, and also they implement strategy because they have a solar array. We just talk about that. They put that on the entire roof, and then a lot of building energy use can be covered by the solar array. So that is a direct current energy. So they use that to directly power the their computers and like monitors and the internal receptacles. So that will save probably the loss from conversion from the AC to DC. Typically, people get a connection from the power grid that is AC, and then they convert that to DC to your computer, then they will lose like 20%. So they eliminated that loss. That also the reduce the energy use from the receptacle equipment. This that's something like good for or start to be considered for like a lot of net zero buildings because they use a lot of generated energy from like PVs, and then they can directly support AC to the building. So that's something they also considered. So this building finally also achieved the net zero. So they put a penthouse level roof, and all of the penthouse roof covered by the PV. So it shows here. So and then they use the energy simulation. They can cover all the energy use of this portion of the offset by the renewable energy use. Another example, just a short example, I want to share is from a building company I worked previously. They're a green building consultant, so they really like the abundance thinking approach, and they are like a pioneer for green building and design in the US. So here is an example. It's called a tower as a PNC Plaza. It's an office high-rise building. So I just show the example for like consider the abundance thinking. Another example of abundance. So So the solution comes from the combination of what is there and not what is missing. So at the beginning of the schematic design stage, they typically will, for a green building or energy efficient design, like an integrated design, we will hold a eco thread, just a name of the meeting, like all people discipline of thresholders come together to think about the strategies. So at the beginning, the owner just say they want a very green, super green building, but with a very limited budget or typical budget. They can so that aims very high, but with a typical budget. So they so that directly eliminate some strategies like purchase like renewable energy or install renewable energy system on site because there's that costs. So so they need to think about more efficient ways to do that. So they just list what is abundant for this building. They are solar radiation on this site, and also they have a massive amount of solar exposure just because it's a high-rise building, and the building is high. That is also considered as abundance, and their facade. The owner really like to invest most of the money on the facade, and also they have a pretty good team, and also good occupants. They are want to cooperate, so they list this and think about the strategies. So they want to use the solar energy and the height to power natural ventilated system in a high-rise building. So that's not often used. So they raise the height of at the top and then use the heat from sun to heat the air here. So causing the air to rise and pull the air below from here and pull the air from outside. So basically it's really a big stack system for the building, stack ventilation. So they implement that, use a double skin facade. So because in high-rise, there are a lot of draft concerns if you only have one single skin for natural ventilation. So to implement the natural ventilation, definitely consider double skin. And so that's how they design, implement that, and to make use of the what they have to achieve their goal. So so that's another example. Yeah, so so these case study I just want because they just want to show the what they typically do and how to consider like when you're doing energy efficient design, just try the direction and like to consider consider what you have and try to think about innovative strategies, and also try to do more analysis at the beginning or in the early design phase, and also definitely in the middle also probably for more detailed analysis, but want probably consider do more at the beginning to that will definitely help to reduce the cost for in the future for like a later stage if there are any change or definitely you have a simulations to support your design decisions rather than just think about it. It probably work, but probably not. So like use a simulation or some simulation is a very cost-effective tool to see if the strategy work. And next, I will talk about more related topics. Yeah, we already have 30 minutes, so I'll just quickly wrap it up. So that's more about the greenhouse gas emissions and the related. Oh, why it won't go? Okay. Yeah, for renewable energy certificates and carbon offsets, that's probably you also familiar with that, but I just want to mention that because it's more and more used because people, organizations, even countries that they consider the carbon neutral and more go for the direction of renewable energy and carbon neutral. And so for renewable certificates, and that's individuals and corporations, they won't unable to install a renewable energy system by themselves. So they probably so as a result they will just want to purchase those renewable energy certificates, and they also purchase carbon offsets to neutralize their energy carbon use to reduce greenhouse gas emissions. So here is the so what is the renewable energy certificates? So that is called the attributes of renewable electricity, because for the grid, for your power grid, there are lots of source like a power plant, like a traditional energy source and a renewable energy source. They all go into the power pool, so they mix together. So how do you claim you use a renewable? Because you get in the mix just as like water. So so separately, they separate the renewable attributes with the energy itself. So if you purchase renewable certificates, then the amount of energy used will be related to that renewable certificate will be identified as green, as a renewable. So that's how they identify the renewable electricity from grid. So people, for example, your company will claim 100% renewable from the power grid. Then they just purchase the renewable energy certificate to offset 100% your annual energy use. So that's the one way to do that. Instead of you install like PVs on your roof, that's a lot of investment, or you purchase a nearby solar farm, purchase energy from them, or you own rent a lease, like a rent a solar farm, something like that. So so that's are not easy to handle solution for involving renewable energy. So that will also help to those development of a renewable energy generation. Yeah, this one I can't, because there are no sound, I just skip that. I already explained that in the last slides. So that one is a better explanation and more detailed explanation of how this ICs work. So they just are instrument that electricity consumers to use to label, to make as an attribute of renewable. Yeah, it kind of work. So so another concept is how green is your power grid. So it depends how many, how much renewable supplier to the grid. What's the percentage of traditional fossil fuel generation versus the renewable generation. So a lot of movement toward the greener power grid. For example, the U.S. Their power grid, there are different regions. You can see a lot of difference in their how green their power measured based on CO2 emissions. So like upstate New York, they have very low, but something like in I think that's Hawaii, so that's much higher, and some location like Gulf Coast and the Midwest that will be higher. So the U.S. average is this number. It's not very, still a lot of traditional power emissions, fuel emissions. Carbon offsets, it's a different than renewable energy. It's it's also tradable commodities, representing the 1 ton of our CO2 emissions reductions. They represent the real emissions reduction have been independently verified that projects that would have happened in a business as usual scenario. So carbon offsets has a lot more diversified or type of a project compared to renewable energy. They just a renewable energy, but the carbon offsets, they also could come from renewable energy, but from all kinds of projects they reduce the carbon. So that's markets, that there is a market to exchange those carbon offsets. So we want to introduce about those projects. So they just give you more information. So when you purchase carbon offsets, you probably want to know what kind of project they come from and if that is verified. Typical carbon offsets project types like forestry and conservation, energy efficiency projects, renewable energy project, waste to energy transportation. There is a lot of, these are just most used. For example, our project standard called verified carbon standard, that's probably #1 widely used project carbon offset project standards. So it has a lot of categories for the projects type. So for transportation, they have things like methodology for carpooling that even consider carbon offsets because they reduce the use of vehicles, and fuel switch from gasoline to ethanol. That's also considered carbon offsets projects. So there are a lot of variety. So that's caused the issue like how they definitely better than renewable energy because they cover a lot. So you can get different the reduction process also to use, and then but they have need more verification. So to make sure these projects really reduce, right? So there were some criteria, several 5 criteria called the paver. So they should be permanent. They cannot be reversed. and they all need to be additional. That means the carbon offset project must be beyond the business as usual. So that be beyond the typical practice, standard practice, has to be present a change in behavior in to spur by buyers at the offset market in order for those buyers to claim to reducing. So that's beyond the standard practice, and they need to be verified. just because they are so lot of varieties that were widely whether they work or not, so they need to be verified, and they need to be enforceable. Emission reduction must be backed by contracts or legal instruments that define their creation to ensure exclusive ownership, and then they need to be real. The carbon offset must not be like incomplete or some artificial thing, but or are technically flawed. So the methodology is published here. They must to follow. They can be like a wrong methodology. They lead to unreal reduction. So that's something. So if by carbon offset, by certified or carbon offsets, so there are some like verified and certified that ensure your purchase is real and meets all these requirements. And so to offset your emissions or energy use, emissions are actually greenhouse gas emissions. There are three types of scope. So carbon offsets can be used for scope 1. It's like a combustion in your boilers, furnace, and the vehicles. So that's directly emission from your own resource. So that is for mostly it's just fossil fuel. It's a carbon offsets can do it. For electricity emissions, you can use the renewable energy to offset that certificates or carbon offset, because carbon offsets can offset everything because it's a emission reduction. And for business travel, like that kind of thing, it's a carbon offsets. Okay, so other things I would talk about rating green building design and that covers energy efficient design framework. One is leadership in energy and environmental design. That provides framework for like healthy, efficient, carbon and cost-effective, energy efficient buildings. It's a globally recognized symbol of accessibility achievement and leadership. There are a lot of, I think a lot of, I don't know how much. Typically, there are at least a few framework or rating systems. You don't have to certify that by using those rating system like LEED to get a LEED certification, but definitely their framework is a very useful tool for you to consider your energy efficient design and all your sustainable design. They have a lot of credits. Each credit has a covers some aspect of the area. So it's pretty well developed and full spectrum framework to consider. You can look at that and to see if some strategies might be useful and how it perform, how to evaluate the performance. So that's very good framework to use to guide your design. Other rating system like there is England, there's I don't remember exact name. Yeah, there's several other widely used system. Some countries they have developed their own framework. So for LEED, there's these symbols are their categories. This is integrative design. This is transportation, site, water, energy, material, indoor air quality, innovation design, and regional priority. That is a typical scorecard of a LEED. So you can see in each category, there are their credits. So that's covers one area of sustainable design. For energy, you see that they have a commissioning requirements. They have energy performance, which covers a lot of weighting of this. That's a kind of combine all the energy performance consideration of the building. And they have a enhanced commissioning, metering, demand response, renewable energy, and also refrigerant management to reduce greenhouse gas emission, and green power and carbon offsets we just introduced. These are covers all like a typical consideration for energy and the atmosphere. And the innovation category, actually, they have it's not separate list here. There are a lot of innovation strategies and also called pilot credits, like strategies that's already developed. So you probably consider, if you go to their website, and you can see the innovation category and the pilot the category. There are some strategies maybe choose to use it and implement in your project, so you can use this as your framework for your design. It also explained a lot. Their online reference guide and explain the approach, how to evaluate that, how to calculate that. There are tools to calculate the performance and for example, water savings and things like that, and the resource. So for lead, they just want the framework, like just want to push the market to shift to our like more, because typical building like 70% is like just standard practice, right? They want to use upgrade their standard to like keep it above, beyond the standard practice to some levels, and to push the market to shift to more green the direction. So when the standard practice just go more green, and then they just change their version, like get more stringent, add more component to that. And the data is back up with the building standard, like performance, like ASHRAE, energy performance standards, some and other standards. So standard version change, lead also change the version, so add more. So with the version change, they will lift and push the market to the better degree of green. So in the green area rather than the yellow area. The rating system, including like new buildings, several categories like new building, new interior, exist building and space, neighborhood development, cities, communities, residential, and their recertification. So these are, for your project, you probably won't like to go inside to see it's near anything you can use for your design to borrow. That's definitely some good resource, even you don't want to certify your building. Another one we'd like to introduce is the Edge software. Edge certification. They can this much less simpler and less complicated than LEED, and easy to use by, like, for example, smaller buildings, probably, and more like cost effective to certify. There's a cost effective way to incorporate energy and water savings options to like the building type they cover, like homes, hotels, hospital, office, and retail space. They cover mainly this type of building. they have a build in their software. They have a software like to evaluate your building that they build with the climate cost data, consumption pattern. They have everything built. So they have like a very user friendly interface. When you just input parameters, and and then the software will give you some real-time indication of is that how much it saves, how it perform. So they have a database, so they just use that rather than use like a very like a detailed simulation like LEED, and they just based on their calculations to do that. They probably not like that detail, but they definitely give you a good feedback of based on the input information. Yeah, I probably still cannot show the I don't know the sound. I don't know how to make it work, but I probably can show. This video shows how the Edge software works. So whoops. Oops. Oh gosh. Oh, it doesn't work. Let me